By the end of this video, you should be able to use a student-constructed manometer to determine the pressure of an enclosed gas. You will need Gas's video number 3 worksheet and a pencil. It also would be encouraged to have a calculator handy so you can try out some of the problems on your own and then check your work with what we do later on in the video. A sample question would be, if the atmospheric pressure is 745 millimeters of mercury, what is the total pressure of all the enclosed gases? Now, atmospheric pressure is something that you had to find from the weather report, either the computer internet channel or perhaps the TV or radio. What you're going to instruct in the class is using a gas collecting tube, closed ends at the top, open ends at the bottom. You're going to put it into a graduated cylinder. At the beginning, the entire graduated cylinder would be full of water. But as the reaction proceeds and the gas is collected, the gas is going to push the water down into your graduated cylinder and out of your gas collecting tube or eudiometer tube. When you're done, on the inside of the tube will be some number of gases. And those gases are going to have a pressure because they're going to be pushing down on the water from inside the tube and forcing the water down and outside the tube and into the graduated cylinder. At the same time, out here, we have air from the atmosphere pushing down into the graduated cylinder. We're going to call that our PATM for atmospheric pressure. This atmospheric pressure is also pushing down onto the water inside the graduated cylinder and pushing it up into the glass collecting tube. So we have two forces occurring at the same time, the pressure of the gases and the pressure of the ATM. In this case, the pressure of the gases is less than the pressure of the atmosphere. The reason why the gases have a lower pressure is because the atmosphere is doing a better job of pushing down than the gases. The gases only push the water down to this level, but the atmosphere presses it down to a lower level. In order to find the difference between these two, you need a height correction factor. This is going to be done using a ruler. So you're going to use the ruler and find the difference in height from the water level in the graduated cylinder to the water level in the eudiometer tube. And you're going to write down what that value is. However, that height, which you can find in millimeters, because you have millimeters on your ruler, will be in H2O and not in mercury, because we're going to be using water. The reason why is water is cheap, it's easy to be had, but also mercury is a toxic substance that can cause health problems down the road. So we don't use mercury, we use water. But now we need to convert this number into millimeters of mercury. You do that by dividing by 13.6. The reason for the 13.6. Mercury is about 13.6 times denser than water. So water will travel 13.6 times further. It takes less energy to move it. Mercury will travel 13.6 times less far. So we're going to divide the two numbers, and when we're done dividing the two numbers, we get a new height correction factor of 3.82 millimeters of mercury. Now let's use that up here. We already said the pressure of the gases was greater than the pressure of the atmosphere. In other words, pressure of the gases equals pressure of the atmosphere minus this height correction factor. The reason for the minusing of the height correction factor is the atmosphere is greater than the gases. If we subtract it out, the two values become the same. So now we're going to plug in our values. Pressure of the gas equals the 745 millimeters of Hg, which we had from the atmosphere up above, minus the 3.82 millimeters Hg, which is our height correction factor. And after we are done subtracting the two from each other, we find the pressure of the gases equals 745 minus 3.82 equals about 741 millimeters of each G. This is a rounded value based on significant figures. If you put down 741.18, that would be fine too. Okay, let's try this in a different way. In this case, the gases were higher up. But what happens if this water level is down low? We're going to use the same basic question. If the atmospheric pressure is 745 millimeters of mercury, remember this has to be found every day based on that day's air pressure. What is the total pressure of the enclosed gases? Now, as before, you want to find your height correction factor. Now, the height here was 75 millimeters of water, but you notice I'm dividing by 13.6. The reason why is, this is water, this is mercury. I need them to be the same. So my height factor now becomes 5.5 millimeters of mercury. Mercury does not travel as far because it is more dense. Okay, go ahead, stop the video, try your problem, and then come back and double check your work. Okay, pressure of the gases, in this case, is greater than pressure of the atmosphere. The reason why, the gases inside here are pushing down better than the air or the atmosphere is pushing down out here. So the gases have more pressure. To make them equal, I want to do pressure of the atmosphere plus my height factor. So pressure of the gases equals my 745 millimeters Hg plus the 5.5 millimeters of mercury correction factor. And when I'm done, pressure of my gases is going to be about 751 millimeters Hg after I'm done rounding for significant figures. Overall, my equation is that the pressure of my gas equals pressure of the atmosphere, and then either plus or minus the height factor after you divide by 13.6. The 13.6 is there if the height factor was in water and you need to convert. You should know when to add and when to subtract. If you're not sure, you want to go back and double check this video, because next time in class we're going to do the Boyle's Law Lab. The Boyle's Law Lab is going to show how pressure and volume are related to each other. So it's going to be imperative that you know how to use this equation.